This is the Science Show with Dr. Dada. It's just so nice, you cannot do without. This is the Science Show with Dr. Dada. It's just so nice, you cannot do without.
Hello, and welcome to the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. Glasgow happens to be very, very glorious and sunny today, and we're really loving it. Well, I'm your host, Dr. Adetunmise Dada, and on this show, we're all about STEM, science, technology, engineering, and mathematics. And today, we'll be tackling a topic that might just spark a revolution in how we power our world and how we protect our planet. So, as you know, we love interviews on this show. We love to bring in experts in various fields to explain how things work in the world of science, and especially to explain how these developments in science affect our everyday lives. And today will be such a show. We promise fun, we promise fascination, and above all, we promise to make the complex things crystal clear and do so in the language that you prefer. Great. So today we have a program brimming with excitement, and we have the privilege of welcoming in our studio Dr. Kaveh Delfanazari. Did I say that right, Kaveh? Yes, you're welcome to today's show. It's really nice to have you with us in the studio. Well, Dr. Kaveh Delfanazari is at the forefront of research that is blending the boundaries of advanced quantum mechanics and practical sustainable technology. He is currently at the University of Glasgow, and he is a senior lecturer or associate professor there, and he's in the ENE, that is Electronic and Nanoscale Engineering Research Division within the James Watt School of Engineering. Now, he's known for some groundbreaking work in hybrid semiconducting and superconducting materials, and he also leads the development of next generation quantum devices. He's been recognized by the Royal Academy of Engineering. He holds a Leverhulme Trust Research Fellowship, and also recognized by the Royal Society of Edinburgh through a personal research fellowship. And that's just to name a few. So you can be sure that we have an expert in the studio, and we'll have things explained in a really, really nice way. Fantastic. So now, before we go into a full interview with Dr. Delfanazari, we're going to be enjoying our news highlights for this week. So the first headline that we have is something very interesting, actually some good news from the world of medical engineering and organic chemistry. So that is about a new class of antibiotics that has been discovered. Scientists at Uppsala University in Sweden have discovered a potent new class of antibiotics effective against drug-resistant bacteria. And this new class of antibiotics show promising effectiveness against multi-drug resistant bacteria. Now, this kind of bacteria has been pinpointed by the WHO, the World Health Organization, as the most critical ones to develop novel treatments for. And so this new antibiotic could be a crucial weapon in the global fight against antibiotic resistance. This discovery is not just pivotal for its immediate implications in treating infections that are currently difficult to manage and treat, but also it sets a foundation for future antibiotic development. So it's very, very interesting research highlighted for its potential to save millions of lives. And in that picture there, that's the photo of the scientist behind this discovery. So Anders Carlsen, in the center of the picture there, is a professor at the Department of Medicinal Chemistry at Uppsala University. And he said, and I quote, that our compound can cure bloodstream infection in mice models indicates great potential. So that's quite interesting. So, of course, a lot of more research needs to be done for that drug to become available for the public. But this is very good news indeed. You can read about this research. It's published in Proceedings of the National Academy of Sciences, PNAS, and the title of the article is a mouthful. I'm not going to try to say it. It starts with antibiotic class with potent in vivo activity targeting lipopolysaccharide synthesis in gram-negative bacteria. Yeah, that's it. Something like that. But you can read more about that in the publication. Great. So the next item on our highlights for today is about something very interesting, something you've heard about before probably. We probably know about graphene. Graphene won the Nobel Prize a few years ago. Now there is something called goldene. I'm sure you can guess what that is. Graphene is like a thin layer, a monoatomic layer of carbon, right? Goldene, as the name probably suggests, is a monoatomic two-dimensional layer of gold, and that's been synthesized for the first time. So researchers have managed to create these sheets of gold that are only one atom thick, and this is also published research in Nature Synthesis and by Kashiwaya et al. So this is something that's really interesting. The title is Synthesis of Goldene Comprising Single Atom Layer Gold. Now, this is a remarkable feat in nanomaterials. It required very, very careful and very, very innovative methods to actually achieve this. So why is goldene interesting? Well, this ultra thin material represents a breakthrough in the field of material science because it promises new applications in electronics, in optics, and in quantum technologies as well. And that kind of ties in with what we're going to be talking about today with Dr. Delfanazari. Now, the unique properties of goldene include things like conductivity, high conductivity, transparency, and this makes it ideal for enhancing the performance and miniaturization of electronic devices. So the fact that they're able to manipulate gold at such a microscopic scale is something that could lead to advancement in fields like flexible electronics. That's also something that we've talked about on the show in the past, and even things like more efficient solar cells and also next generation optical devices. So this is very, very exciting indeed. I'm sure you'll agree. So goldene, we can say, is a cousin of graphene, and who knows, maybe it's going to win a Nobel Prize sometime in the future as well, depending on how the applications how useful they prove to be. Great. So the third and last highlight that we're going to be considering today is about a black hole, a large stellar black hole. A new one has been identified. Now, astronomers have discovered this, what's considered the most massive stellar black hole in our galaxy. And this is also published, research is published in the Astronomy and Astrophysics journal. Now, this discovery, you can say, is groundbreaking because it's within our Milky Way galaxy. And this is, as we said, the largest stellar black hole to date. It's called Gaia BH3, Gaia BH3. And it's about 33 times the mass of our sun. That's significantly heavier than previously found black holes within the stellar classes. Now, typically a stellar black hole is one that's formed from the remnants of a massive star's supernova explosion. And the size and characteristics of this particular black hole could lead to new insights into the life cycle of massive stars and the dynamics of our galaxy. So this is a very, very interesting research that came about from collaboration of many, many scientists from different parts of the world, and they had a lot of interesting things to say about it. So before this black hole, the most impressive black hole in the Milky Way galaxy was Sagittarius A, and this has the combined mass of several million suns. But this is a different kind of black hole. This is a very interesting result. And that wraps up our news highlights for today. Now, each of these developments, you'll agree, is something that shows the beauty and brilliance of modern science, because it's just amazing to be able to actually do these research, to find out these things, be it discovering new drugs, to making devices that were not possible in the past possible, to discovering new things about our universe. These are all things that are very, very interesting for us indeed. Make you think. They make you think and make you wonder, don't they? Great. So now we're back to our guest, Dr. Delfa Nazari. Once again, it's really, really a pleasure to have you with us in the studio today at Cave. Great. So let's perhaps get to know you a little bit through this interview. Could you tell us about the moment or about the experience that moved you to develop an interest and passion in quantum technologies and maybe STEM in general?
Okay, hello. It's a great pleasure to be here, actually.
Yes.
Thanks so much for having me here today, Dr. Dada. As you mentioned earlier, so basically I started my career in quantum technologies since my PhD time,
Yes.
actually in a quantum nanoarchitectonic group at the University of Tsukuba in Japan.
Wow.
So where I had the privilege to work with leading basically high temperature superconductivity scientists. So basically that triggered my interest in superconductivity and quantum devices and circuit based on superconductors.
Wow, that's amazing. And before that, what was it like for you getting into STEM? So did you study in Japan for your school, your primary school, secondary school, or was it in a different country?
Yeah, actually it was different country. So I was born and grown up in northern Iran,
I see.
and then I did basically the schools and the first grade of university in basically northern Iran and also in capital Tehran.
I see.
Before I moved to Japan, actually for my PhD degree in superconductivity and superconducting devices.
Wow, that's amazing. So what was the track like for you? So you did your primary school, secondary school, then you went to university in Japan?
No,
or did you do
basically it was in Tehran.
In Tehran.
Yeah.
Nice. And after that, you went straight for PhD. Did you do an MSc
Yes,
in between?
MSc, yeah.
I see. Was that in Iran as well?
Yeah.
I see. Wow, fantastic. I have a friend from Iran. I met him in Sweden. His name is Ahmed Panahi. So if Ahmed is listening, shout out to Ahmed. He's really, really good friend of mine back then when I was doing a master's in KTH in Sweden.
I see.
Good. So now your research, of course, has led to work in diverse environments. So Japan, UK. How would you say these varied sort of cultural backgrounds have influenced your research ethos and your vision for, what drives your research at the moment?
Yeah, actually, I was quite lucky to work in the group. Actually, I did my PhD because we were, that time my supervisor had an international project and multiple universities from Japan and outside the Japan, US, Turkey, Germany, they were involved. So basically, I started international collaboration since beginning of my PhD. And then when I moved to UK to work actually as a research fellow first in University of Southampton, again the environment was quite international and quite diverse. Basically, research activities were going on there, and it was fantastic. So I could develop my collaboration, my interaction with different basically research group from different country with different skills, with different basically focus, different vision and different backgrounds. So that could help me to develop my vision as well in the research and to get now and also to develop my network in the research and basically to end up to the academic job, which was something which I had the dream for since beginning of my PhD.
That's nice. That's really nice. As we probably know, something in science that's super important is the network, isn't it?
Exactly.
It's collaborative, and you kind of need that network. An international network is invaluable in scientific research these days. Great, fantastic. So, is there any particular achievement or discovery in like quantum technologies that stands out for you? Would you say it doesn't have to be something unknown? Just which discovery in quantum technologies would you say is something that you would like to share with the public that you find very, very particularly interesting?
Yeah, I think I'm quite excited by the nature of superconductivity. It's a quantum phenomena in microscopic scale. So normally quantum effect deals with a small, normally nanostructure, basically system. But superconductivity is a quantum system in large scale, microscopic scale, which can keep the coherence in very large, basically, distance. So that's quite fascinating, I think. And the other thing is the effect which is called Josephson effect, and it actually bases of my fundamental for my research. We do junctions made by superconductors coupled to insulators or semiconductors to form so-called Josephson junctions. That's also very fascinating. So basically, you can get dissipationless current or electricity in a media which has resistivity by its own. So I think that's also very exciting.
Yes, that's amazing, isn't it? It's. We're going to go a little bit more into detail about how that's applied in quantum technologies after the break. I think for now, we're going to take a music break and we're going to listen to a song from the heart of Africa, from Congo. So the song is by Wenger Music and Maison Mère, and it's entitled Kofi Ayana. And we'll be right back. Well, that's a very energetic track, very fitting for the beautiful day, the beautiful sunny day that we have today in the city of Glasgow. And this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. And I would like to take this moment to shout out to our sponsor, IOP Scotland. We'd like to thank the University of Glasgow, where both myself and our guest work, and of course the APSRC and other funding bodies who support our research. And of course, we'd like to also remind you that you can listen to the show on DAB. You can also listen and watch us live at jamboradio.co.uk. Also, episodes are available to watch on demand on our Jambo Radio Scotland channel on YouTube. So, very good. And very soon, we're going to also have a discussion where you can chip in, you can call and give us your thoughts on the question of the week, which we'll reveal in a moment. But for now, let's get to know Dr. Delfa Nazari's research a little bit better. So, for those of us who are tuning in and maybe find the world of quantum computing a little bit obscure, they don't know what it's about, could you just, break it down in your own way and tell us exactly what your field entails and why it's critical and crucial for our future, would you say?
Yeah, so, just we have computers in our pockets, in our everyday life. I think we work with different type of computers, from mobile phones to basically our PCs or laptops. So, but for some particular calculation, they are limited. Basically, they collapse. So we need a more computational speed, with more basically efficiency as well. So for that, quantum mechanics basically can help us. So quantum computers are normally built on the quantum physics. So in that sense, rather than the normal computer that basically we have logic 0 or 1 at only one time, we can have a 0 and 1 at basically simultaneously.
Yes.
So, but there are different challenges to make a quantum computer. So there are hardware challenges, there are software challenges. We mostly focus on hardware, though we do a little bit with software, basically challenges as well. So there are different platforms for quantum computers. Mostly quantum computers are in the research and development stages. So for mostly hardware side, one of the promising basically platforms are superconducting quantum circuits, which we focus on bringing superconductivity with semiconductors coupled together to benefit from basically unique properties of two different materials in one basically system.
Yeah.
So in that sense, we hope to address some challenges related to scalability, integration, basically stability, and robustness of the quantum computer hardware, especially.
Yes. Yeah. Thank you very much for that. That's a really nice way to put things, isn't it? Very good. Now, graphene is something that you're no stranger to. Could you please break it down for us in a way that is easy for us to understand what graphene is? We kind of mentioned a little bit in the news highlights, but could you mention again what it is and what its role is in the development of these advanced electronics?
So basically, graphene has got a lot of attentions because of some unique properties it provides. So it's a very thin, one layer of carbon, basically, which are arranged in two-dimensional honeycomb structures. So they provide a lot of flexibility and also robustness in the circuits. So they can be tuned by voltage, by basically electrical or optical basically probes, and provide us basically a lot of functionality which we can't get with some of the conventional materials. And they are quite basically robust, they are quite light basically as well, and make the allow the electronics or photonics based circuit to be cost efficient and also to be efficient, power efficient, and the efficiency of the device, which is quite important, actually could be maintained with graphene as one of the advanced material basically platforms.
Wow, that's nice. Very, very good. And this idea of golden, how do you see that, influencing things going forward? So if you do you think it's something that could be useful for your research, for example? And how would you go about using it if you laid your hands on some?
Yeah, I think that's in a very early stage, but the news seems to be quite exciting. I mean, graphene or golden or whatever non-superconducting materials, especially, I mean, I'm talking about my vision from hybrid circuit-based, basically, point of view. So graphene or golden or other type of materials, gold or basically, as I said, non-superconducting materials, which could be metal or basically semiconductor, insulator, and those things. So yeah, I'm looking forward for development in advanced materials. So then when we couple them with superconductors, then we will benefit from unique basically properties of each of these materials. So for example, gold by its own, it's a noble material. It cannot carry electricity without dissipation.
Yeah.
But when we couple gold with superconductors, then we can actually have current passing through the gold dissipation. I mean, without any consumption. So I think that would be quite exciting from a circuit point of view, from power efficiency or reduction of the energy consumption in electrical circuits.
Yes, indeed. Yes. It will be interesting to see how that develops, wouldn't it?
Yeah, exactly.
In quantum computing, what applications will become more available. So that's great, fantastic. Thank you very much for that. Now, before we go on the next music break, can you tell us what kinds of equipment and techniques do you use in your lab that you would consider like cutting edge tools, for example?
Yeah, actually, we require quite advanced tools to make advanced chips and advanced circuits. So we need to have to access to the basically state-of-the-art nanofabrication and microfabrication facilities. So which we are again lucky to have University of Glasgow Nanofabrication Center. So it hosts the state-of-the-art nanofabrication and microfabrication facilities, which our students and basically researchers can benefit from using them. And from characterization and measurement side, superconductors are materials that basically show quantum behavior at low temperature. Certain temperature, or is called critical temperature, depends on the materials. So for that, we need to cool the material down to certain temperatures, normally below 4 Kelvin or even sometimes millikelvin, which is close to absolute zero temperature. So for that, we need to have quite sophisticated equipments. It's called dilution refrigerator or cryostats, that allows us to see the transition from metallic phase to superconducting phase when we cool the system down to certain temperature below the critical temperature.
Wow, that's amazing. Those are, I used to do some research in quantum dots where you had to cool down the samples to 4 Kelvin. But this is much colder. You're talking about much colder temperatures, which is very, very interesting. The kind of devices you get to work with. Very nice toys, you'd say.
Yeah, so actually, sometimes we have the temperature in our lab lower than outer space, actually.
Yes, absolutely.
Outer universe.
So that's a nice perspective on things, isn't it?
Exactly.
So it's colder than outer space. Wow. That's amazing, isn't it? Fantastic. Thanks very much for that. So now what we'll do is we'll go on another music break and we'll be right back. So now we're going to listen to a song by La Prudencia. It's entitled Sabotage. Fantastic. That's another sunny track from Africa and it's entitled Sabotage, La Prudencia. So that's a nice one. Very fitting again for the nice weather that we're enjoying in Glasgow today. And you're welcome back to the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from Glasgow. So now we've come to the section of our show where we're going to discuss the question of the week. So this week, the question we're discussing is very, very interesting. It's about next generation semiconductors, and it is how will next generation semiconductors transform our world? Okay, so we have an expert here who is working really in that field and is going to give us some ideas. But also we want to hear your thoughts. So please feel free to call in. In fact, we'd like to hear your thoughts on this. And you can join the conversation by calling this number 0141 530 2787. And that's 0141 530 2787. So now let's carry on this discussion with Dr. Delfa Nazari. So Dr. Delfa Nazari, as we consider, if you like, the new era in quantum technologies. Could you tell us some what you kind of make some differences between quantum materials and conventional materials? What sets them apart, and how that will change electronics as we know it today?
So yeah, quantum materials basically show some fascinating behavior that we can't see them in conventional materials. So for example, superconductivity. So superconductivity allows us to have dissipation-less electricity,
so zero resistance
forever. So if we can make electronics, for example, out of them, then we save a lot of energy, and that directly addresses the global warming challenges which we face at the moment. So we need less energy to run the electrical circuit, and actually we consume less, so means that we have less carbon out for the basically in the climate, and so that help us in some sort to deal with the global challenges.
I see. That's really interesting. So that's how the green energy aspect ties in.
Exactly.
Interesting. So we could say opening the door to quantum and green tech. So how close are we, would you say then?
So I mean, superconductivity actually has developed quite significantly. Quantum system, quantum devices, the way we develop quantum devices, the way we actually make advanced materials, semiconductor, superconductor, even insulators and other type of new materials. So we have a lot of advancement in fabrication technologies, and also in basically transforming them, using them in novel technologies like quantum communication, for example. We can communicate unconditionally secured way. So that has a lot of impact in our everyday life as well. Or from other side, for example, MRIs are based on superconducting materials. So then the magnet there requires a lot of power consumption if we use normal magnets. But again, superconductors allows us to make very high magnetic field, but with very low basically power consumption, to enable us to make very accurate images of our body or our brains, for example. And again, that has direct impact in our life. From that sense, computing, for example, drug discovery, if we make quantum computers, drug discovery, material discovery will be totally basically revolutionized with high speed and also efficient way of computations.
Yeah, absolutely. So these are really big challenges and big promises, isn't it? So it's really exciting. We wish you all the best with your research, and of course your research is at the interface of the sort of quantum science and these practical applications. So it's really exciting indeed.
Thank you.
So as we look forward to a greener and more technologically advanced and sustainable society, can you share a development from your own sort of work, your recent work, that you believe has the potential to contribute to this impact on our approach to energy and resource conservation and such similar topics?
Yeah, so as I mentioned, we focused on developing hardware, and our focus, for example, for hardware, we want to test them in low temperature, as I mentioned, requires for superconductivity. And then if you want to test one device per each cool down, then it takes us a lot of time, energy, and we need to burn a lot of power to reach to that low temperature and so on. But we try to make many devices in basically single chip, and we study their reproducibility, their robustness, and their basically electrical and basically optical response in
Yes.
low temperature in a very large scale. So, for example, rather than cooling down 200 times, we
Yeah.
cool down only once, but we measure 200 devices at one cool down.
I see.
So in this way, we try to save a lot of time, energy, and also to look at the same time to some challenges like integration or scalability. And from other side, for a quantum computer to work, basically, we need to, again, power consumption or heat generation
Yeah.
is not only is a problem from carbon generation point of view, but from other side, heat generation will kill the quantum states
Yes.
of the quantum devices. So we don't want them in our quantum system.
True.
So
I
again,
see.
we try to work on hardwares that requires energy. Basically, they can be integrated with the quantum devices at the same place, rather than relying on the external, for example, electronics from the cryostat, which quantum processors are based there. So in this case, again, we save a lot of energy. We address the heat and noise challenges of the quantum systems.
Great.
And finally, we work on generation of the coherent light sources on chip. So normally to have light sources, especially coherent one, that basically could be used in quantum computing or quantum communication, in general quantum information processing, they require sophisticated or bulky lasers or electronics, tabletop basically equipment. But we try to generate basically and integrate quantum light sources on chip.
Yes.
And then they can be operated at the same time, at the same place with
Yes.
quantum processors.
Yes.
So again, addressing some of the challenges of integration, especially with the quantum computer.
Fantastic. Great news. All these things are great news for quantum technologies, for sure. Fantastic. Thank you so much for sharing those perspectives with us.
Thank you.
And, well, I'm afraid that's all time is going to allow us to do in this discussion today. And what we'll do is we'll take another music break briefly for a minute or two, and we'll listen to a song entitled Amulanga by Magic System, and we'll be right back. Well, that's Amulanga by Magic System, and this is the Science Show on Jambo Radio, broadcasting live from Glasgow. We've been discussing and we've been having a very enlightening chat with our visitor today, our guest, Dr. Kabe Delfanazari. We'll be talking about quantum technology, superconductivity, and so on and so forth. And it's been really nice. But now what we're going to do is, to conclude the show today, we're going to vibe to some what you call some science beats, or the STEM beat of the week. And that is something to do with one of our news items, and that's black holes. So you probably heard this beat before on this show, but now it's been kind of developed a little bit further. So there's some lyrics on it now. And what we're going to do is we're going to ask our producer to DJ to play the song through for us, and we'll talk about what it says in what follows next. Let's listen.
Let's go. Let's go. Let's go. Don't even know what I am. I swallow a massive star. Don't even know what I'm about. I swallow a neutral star. I'm a beast. I'm a monster. I swallow a massive star. I'm a beast. I'm a monster. I pop a jet of gas. Freezing cold on the inside. Incredibly hot just outside. I'm gonna bend your mind. Even your space and time. If you come any closer, you will be spaghettified. Hit you like a bulldozer. Look at the butt of the pie.
Thank you very much, DJ, for playing that. So let's pause it there. And so this is a bit of a riddle as well. So did you notice what it says in the lyrics? Those of us listening as well online and on the radio. So it says, don't even know what I am, I swallow a massive star. Don't even know what I am, I swallow neutron stars. I'm a beast, I'm a monster. I swallow a massive star. I'm a beast, I'm a monster. I burp a jet of gas. So what am I? Maybe that's a quiz for everyone. So who's speaking then? Perhaps there's a lot of hints. There's a lot of physics in there as well. Perhaps Dr. Kave Delfanazari, any ideas what is speaking or who it is?
Not unfortunately.
No. Anyway, if anyone knows online and would like to call in to let us know, that would be great as well. But I might as well just say what it is. So you'll notice it says swallow a massive star. So in the cosmos, there is an object. We mentioned it in the news today. There's an object that swallows stars. Well,
Black hole.
it's a black hole. Yes, that's it. It's a black hole. So yes, and yeah, I'm still looking for a name for that track and another verse for it. So tune in for future episodes and you can hear maybe more bars and lines on that song. So yes, it's a black hole. It says it swallows neutron stars, black holes swallow everything. Black holes swallow other black holes. And it also says it's a beast. Of course, it's a beast and a monster, like the one we have in the center of our Milky Way galaxy. It's so huge and everything revolves around it and so on. And then it says, I burp a jet of gas. Sometimes that happens when black holes swallow big stars and, sometimes you get a jet coming out of the black hole. So this is all kind of playing around with the physics, is some of the phenomena we observe in the cosmos. And then something else it says, if you come any closer, you will be spaghettified. Of course, we know that's what happens when, if something goes to the black hole because of the bending of space and time and the immense gravity in the black hole, there's something called spaghettification, which means the thing just gets drawn into a very thin line, just like, a spaghetti, and so on and so forth. So there's a lot to unpack there. But I can promise we'll listen to that again on a future episode of the show. And with that, we'd like to call it a day on today's episode of the Science Show with Dr. Dada on Jambo Radio Scotland. We'd love to hear from you. Please do share your thoughts and questions with us. And stay tuned, stay locked on this show to keep up with the breakthrough and impact of daily life that science is having. And I'd like to say a big thank you to you for tuning in to this week's edition and to our sponsors and to everyone here at Jambo Radio Scotland. And with that, this is Dr. Dada signing off. Until next time, stay curious.